Happy learning! Today we're going to work on project scheduling. Okay, so in our last video, we focused on finding the shortest path from one vertex to another. So today we will still focus on finding a specific path. But we're no longer interested in the shortest path. We're interested in something slightly different. We're going to search for something known as the critical path. All right, so we're going to have to define what the critical path is in a little bit. But basically, the types of problems we're going to look at today is when you have a bunch of tasks you need to complete, but some tasks depend on the completion of other tasks. So for instance, if you're hosting a party, one of your tasks might be buy the food, and another task might be cook the food, right? But you can't cook the food until you finished buying the food. All right, so the buying task would have to happen before the cooking task. All right, and so what we're going to use, so to visualize the relation between tasks, we're going to use directed graphs. Remember, a directed graph is just like a graph, but we have little arrows or arcs instead of edges. So we will use directed graphs where the vertices are the tasks. And an arc from A to B means that task A must be completed before task B. And it's not just that task A has to be completed before task B is completed. It has to be completed before task B could even begin, right? You have to have the food purchased before you could even start cooking the food. All right, so let me give you an example of how this is going to look. All right, so suppose we have a bunch of tasks, and there's some time to complete the tasks. All right, so we're going to have the just the vertices, the time it takes to complete the task, and then also what tasks have to be completed before that specific vertex could start. So we call that the precedence relation. All right, so here, suppose we have vertex F, and it takes 40, let's say, minutes to complete task F. And we'll have no precedent relation for F. That means we could start F right away. Nothing needs to be completed before F could start. B 20, again with nothing. D 20, again with nothing. V 30, and we'll have a precedence relations of D. Okay, that means task D needs to be completed before task V can start. All right, here we have task S that has two things that need to be completed before it could be started, which that's okay. And then finally task T, V and C. Okay, we want to take this table and represent it as a directed graph. And our goal eventually is to figure out how can we complete all of these tasks as quickly as possible. Okay? And also, how many people do we need to help assist in completing these tasks to do it as quickly as possible? All right, so how do we make a directed graph? We're going to have a start vertex and an end vertex that aren't any of these tasks. And I'm going to make a directed graph with the arcs all pointing to the right. It's just going to be easier to keep track of everything. All right, so what tasks can we complete initially? We don't have to wait for anything else to be done. That's F, B, and D. All right, so this is F, B, and D. And what we're also going to do is we're going to write the processing time along with the vertex. So this tells us that F takes 40 minutes, let's say. B takes 20. D takes 20. Okay. V happens once D is completed. C happens once F is completed. So we're going to have an arc from F to C, which was 60. And we'll have an arc from D to V. V is 30. S needs B and C to be completed. Here's B, here's C, so let's put S here. S is 30. And T needs V and C to be completed. Okay? And the last thing is we're going to have a vertex called end, just so we have like a start and an end. So this digraph captures all of the information of our table here. It's just going to be convenient to use a digraph instead of this table. Okay, and so our goal is to figure out how to do these tasks as quickly as possible. And just notice, since F has to happen before C and C has to happen before S, we're going to have, this is just an example, it might not be the best case scenario, but we're going to have at least 40 plus 60 plus 30 minutes of work to be done. Okay, so best case scenario, maybe there's even better than this, but best case 130. Okay, where did I get that? 40 plus 60 plus 30. And so what we're going to look for in the graph is something called the critical path. So let's define the critical path, and then we'll talk about how to find said path. and we will solve all the world's problems. Okay, a critical path is the path with highest total time. Out of all paths that begin at start and end to end. Okay, so we look at all possible paths that begin at start and end to end. The one that has the highest total weight, that's our critical path. And the critical path gives us, the length of the critical path gives us the best case scenario for completing our tasks, for completing all of the tasks. Okay? The critical times which we're going to write as critical time of a vertex x it's defined as the sum of the processing time of x with the maximum of the critical times for all vertices where x points to that vertex. Let me write it down. We'll see an example. So it's the sum of the processing times of x with the max of the critical times. Okay, critical time in both definitions. Maybe it's a little suspicious, but we'll see an example. So trust me. For all vertices y, for which xy is an arc. Okay, let's put this in math. Let's put it in an equation instead of the sentence here. So the critical time of x is equal to the processing time of x. Right, these are our processing times, plus the max of the critical times of y, such that xy is an arc. Okay, the critical time of the end is 0. So the critical time of S would be 30 plus 0. It's going to be 30. The critical time of T is going to be 20 plus 0, which is 20. Okay, the critical time of C is going to be 60 plus the maximum of these two guys. All right, and then we can see we're going to build our critical times basically from right to left. All right, we'll do that in a second. Let me state the critical path algorithm, and then we'll get to doing an example. I'm going to leave this diagram up just because we're going to use it in our example. So I'll write the algorithm here and then move over to this side of the board. All right, so the input for this critical path algorithm, so what do we need in order to use it? We need the digraph with the processing times. All right, so we have our digraph, we have our processing times, we're good to go. First step. Label the vertex end. Big picture. We're going to label each of our vertices. We already have the processing times. We're also going to put a second label with it. That's the critical times. So each vertex is going to have 2 numbers associated with it. So label the vertex end with processing time 0 and critical time 0. Okay? We're going to use the brackets for critical time. We're going to use the parentheses for processing time to keep it straight. Starting at end, we're going to travel across the arcs in reverse order. So we're going to go from right to left. Okay? When we get to a new vertex, we're going to compute its critical time. So calculate critical times. All right, I know it looks intimidating with this max of a set, but it's literally just the processing time of the vertex plus the maximum of the critical times that we've already found for the vertices that we're pointing at. Okay? Once we do that, we're basically done. So that's the hard part, if you want to call it the hard part. So once all critical times have been obtained, okay, what we're going to do is, so once all critical times are obtained, we're going to basically write something called a priority list. Okay, the priority list is going to tell us what tasks we should complete first. What should we put our effort into initially? So write a priority list by ordering the vertices by decreasing critical times. This priority list will guarantee that we'll be able to complete the tasks as efficiently as possible with the number of people that we're going to use to help complete the tasks. Okay, let's work through an example. Let's apply this algorithm to this directed graph. All right, and then we're going to actually create a schedule using 2 people. All right, so once we get our priority list, I'll show you how to actually assign tasks. All right, first step, label the end vertex with processing time 0, critical time 0. Next step, we're basically going to travel the arcs from right to left. S points to end. Its critical time is going to be 30 plus 0, which is 30. T points to end, so its critical time is 20. Okay, C, its critical time is 60 plus the maximum of these two critical times. The max of these two is 30. C's critical time is going to be 90. V's is 30 plus the max of any of the arcs it points to. It only points to T, so it's 30 plus 20, 50. F only points to C, so it's going to be 40 plus 90, 130. B points to S. 20 plus 30 is 50. D points to V. 20 plus 50 is 70. And start gets the critical time that's the biggest of all these, which is 130. Okay, this number, 130, here, let me write it here so it's a little easier to read. 130 says, no matter how many people we have trying to complete these tasks, the best case scenario is we're going to finish in 130 minutes. Okay, so if we could complete these tasks with 3 people in 130 minutes, there's no point in asking a 4th person. It's still going to take 130 minutes. Now, when we do it with 2 people, if it takes 150 minutes, then there's reason to say, let's get one more friend to help us with these tasks. Okay, what is our priority list? Our priority list is going to be, well, we write down our tasks in decreasing order by their critical times. All right, our priority list is going to be, well, start, but we don't really have to include that. F. We don't really need commas either. What's next would be 90, so C. D is 70. B and V are both 50, so we could put them in either order. And then S, T. All right, so this is our priority list. All right, so let's now assign tasks with 2 processors, 2 people completing a task. So let's find a schedule. All right, and so we're going to use this priority list to assign the tasks. So we're going to have processor 1, processor 2, and since all of our times are like multiples of 10, I'll break it up into 10-minute chunks. All right, we know the best case scenario is going to be 130 minutes. Let's see how we do. Maybe it takes a little bit more than 130. Let's see. Okay, so processor 1 is going to take the first task on our priority list, F, and it takes 40 units of time to complete task F. So processor 1 is going to do task F for the first 40 minutes. Processor 2 is going to then try to start task C. Task C cannot start until task F is complete. Okay, so we're going to pass over task C and go to the next task. The next task is D. D can be started, so we're going to start task D instead. So D. I'm going to cross that off of our priority list because we are now completed. Processor 1 is still working hard on task F. Processor 2 is ready for their next task. So again, they're going to try to start task C. But task F has not been completed yet. So we're going to skip over task C again and try task B. Task B is available. So we'll do task B for 20 minutes. Okay, task F has been completed. Task B has been completed. Both processors are ready for their next task. So processor 1 gets task C. C is now eligible to be started, right? Because C needed F to be completed. So C is now eligible. Processor 1 will complete task C in 60 minutes. All right, now processor 2 is looking for their job. C can't be done, or C is already being done, so we're not doing that. What about V? V needed D to be completed, and it's been completed. So we will assign V to processor number 2. Okay. V is now done. Processor 2 is ready for their next task. Well, C is already being worked on. Task S needs C to be completed. And task T also needs C to be completed. So what does processor 2 do? They just chill. They just open up their phone and watch math YouTube videos. All right, so we're going to mark that with a star. So for these 30 minutes, processor 2 has no tasks to complete, so they're just going to wait around. Task C is finally done. And we are ready to hand out the next tasks. All right? What's first on our priority list is S. So processor 1 will get S for 30 minutes, and processor 2 will get T for 20 minutes. All right, and now all the tasks are complete. And it took us 130 minutes. And you might be asking, could it be more efficient to hire more employees to help with these tasks? And the answer is not in this case. Okay, since our 130 matched the critical time of start, no matter how many employees you have, 130 is the best case scenario. Okay, so we actually, with just 2 people, completed all these tasks as efficiently as possible. There are going to be some scenarios where 2 does not hit the critical time of start. Maybe you'd end at 150. And then you would want to try with 3 people, or 4 people, or 5 people. Okay, but in this case, since we got 130 matches with the 130, this is the best case scenario. Okay, I guess we technically could try to do it with 1, but it's not hard to see that it's going to take way more than 130 minutes to do it with 1. Okay, well, I hope you found this video interesting. Let me know in the comments if you have any questions, and I'll see you in the next one. Take care. Bye-bye.